Here are our objectives for 4.1. Okay? Evaluate exponential functions, graph exponential functions, evaluate functions with a base of e, and use compound interest formulas. Okay? So if we are evaluating any function, do you remember what that looks like? If I say f of x equals 2x plus 5, how about if I write a plus? 2x plus 5, how do you find f of 3? How do you evaluate that function? Plug in 3 for x. So we say 2 times 3 plus 5. 2 times 3 is 6 plus 5. So f of 3 is 11. Okay? So that's evaluating functions. Can you evaluate exponential functions? Well, hopefully. If f of x is 2 to the x power plus 5, can we find f of 3? So 2 to the third power plus 5. 2 to the third power is 8. 8 plus 5, 13. Can you evaluate exponential functions? Okay. What if it's a little bit more difficult? Because we could just do that all in our head. What if it was 3.5 times 2.3 to the x power? Can you evaluate f of 4? And if you can, how would you do that? Calculator? Okay. So if I say 3.5, 2.3 raised to the, fourth power. So 97.9444. But remember what's happening is I just raised the 2.3 to the fourth power and then multiplied that by 3.5. Right? The next thing was graphing exponential functions. 2 things I want to remind you about. First of all, there's exponential growth. This is the formula for exponential function. Okay? For it to be growth, b has to be, do you remember? Greater than or equal to 1, right? For it to be decay, what has to happen? Thank you. B has to be between 0 and 1. Okay? So this one would be something like 2 to the x power, right? Or if we had the decay, it would be like this. And that would be something like b would be like a half, right? 1/2 to the x power. Okay? Any questions about that? Typically, we classify exponential growth as an increasing function because from left to right it is increasing. So then typically we would classify decay as decreasing because from left to right it is decreasing, right? Okay? The other thing that you need to make sure that you remember how to do is all the transformations of a function that's exponential. Okay? So for example, if I have f of x equals negative 4 times 1/2 to the x plus 3 power minus 2, I need you to be able to tell me how does that change compared to its parent. Well, first of all, hopefully you can tell that its parent is 1/2 to the x power. Can you tell that? Okay, so what does that cause? That's a reflection, right? Not just a reflection, but a reflection over the x-axis, right? Okay, what kind of change does that cause? So a vertical stretch. By a factor of 4. It's a stretch because it's a vertical stretch because it's on the outside, right? And it's greater than or equal to 1. Not equal to, sorry, just greater than 1. Okay. What does the 1/2 cause? Does it actually cause anything? No, that's like the parent, right? 1/2 to the x power. We talked about that being the parent a second ago. Sometimes people try to make that like do something to the function. But in fact, that's just part of the parent function. Okay? What does that 3 cause? It is horizontal shift, left 3, and it's horizontal because it is inside the function, right? When we're talking about an exponent, we're talking about inside of the exponent or outside of the exponent. And what kind of change does this cause right here? Okay. Vertical shift down 2. And it's vertical because it's outside, right? Outside of the equation. Parent function wise, this would look like this, right? That's decay because b is between 0 and 1. Okay? If I took this and I reflected it over the x-axis, it would be this way. What point on this graph is the easiest to move? Do you know? The y-intercept is actually the easiest to move because it's going to cross at 0, 1, right? Because anything to the 0 power is 1, so that's the easiest point to move. So if we reflect it across, it's going to be this way, right? And then we stretched it by a factor of 4, so it's going to be much steeper, like this. And then we moved it left 3. 1, 2, 3, so it's over like this. And then we moved it down 2. So it's going to end up looking something like that, with all of the different shifts and stretches and stuff like that that we just did to it. What? It's not, though, because it's a reflection. It's not growth because it's actually it's almost more like almost like a logarithmic one, although it's not, because it's just a reflection of a decay. So it's a reflection over the x-axis, which is why it's not logarithmic, because that's a reflection over y equals x, because of the fact that those are inverse functions. So similar, but not exactly. Okay. Do you remember talking about this number in Algebra 2? Remember, at that time I told you that your whole life people have told you that was a letter. And that's true because it is. Okay? But in Algebra 2, in mathematical circles, we use that as a representation of a number. And it's not a variable. It doesn't change. The value of e doesn't change. 2.818 and then 281827, if you want to know that many decimal places. This is what I usually try to remember, 2.8. What? Oh, well, it would help if I wrote it down correctly. That would help. 2.718. Okay? If you ever just really want to know it, it's actually on your calculator right here. And you can press e to the first power, 2.71828. It'll just tell you right off the bat. Okay? So yeah, you're right. It's definitely a 7. I just wrote it wrong. Thank you for being patient. Okay? So another thing we have to be able to do as far as our objectives today are evaluate functions with base e. So it's basically just saying, like we talked about at the beginning, right here. If you can evaluate a function, you can evaluate an exponent. You should be able to evaluate it even if it has something like that. Okay? We should be able to find f of 2. And we find f of 2 by saying 5 times 2. So it's just e to the 10th. Because 5 times 2 is 10. So 4 times e to the 10th power then would be 88,105.9-ish. It's rounded. Okay? Does that make sense? Okay. Last thing in our objective today is talking about compound interest formulas. We did quite a bit of this in Algebra 2, so I'm just going to remind you of the formulas, if that's all right. Unless you just already have them memorized. Oh, that's a no? Okay. That's one compound interest formula. And that's another compound interest formula. Okay? This compound interest formula is if it is compounded a certain number of times. Like if it's compounded quarterly or compounded monthly or compounded daily, something like that. This is the formula we use if it's compounded continuously. What do I mean compounded? With what's compounded a number of times, or what's compounded continuously? The interest. Okay? So just to make sure you remember what all these letters mean, A is going to be the amount, but specifically the amount that you end with. Okay? P is going to be the principal. Whoops. Or the amount you start with. R is going to be your rate, your interest rate. The most important thing you have to remember about this is it's going to say something like 3% or 5%. And when you actually put that in the problem, you have to put it as its decimal equivalent. You can't just put in 3. You got to put in 0.03 or 0.12 if it's 12%. Something like that, okay? T is our time. And in these particular formulas right here, we always measure our time in years. Unless it specifically says something else, but even then, it's typically years. Okay? And then N is the number of times per year that the interest is compounded. So a lot of times we see yearly. How many times a year is it compounded if it's yearly? Once. What about monthly? And weekly? 52. Another common one is quarterly. What do you think about that? 4. Okay. Any questions about any of that? Okay. I didn't show you any examples of that. Do I need to show you examples of this? We did quite a bit of it in class last year, right? So I thought maybe you would remember, but if not, I don't mind showing you examples. Or if you need help, you can just ask me. Is that fair? Okay. Okay. So that is 4.1.